Hello everyone, welcome back to ECE350 lecture 22. We're going to talk about, in this lecture, we're going to talk about plane wave propagation in lossy media and power density. So this is the equation for our wave propagation, right? Plane wave propagation. And you know the gamma is alpha plus j beta. Alpha is the propagation constant and beta is the phase constant. So for alpha in a lossy media, is a long equation here. This is the alpha for lossy media and this is the beta for lossy media. So you know that you have mu is a permeability and omega is the frequency in radian per seconds, and your epsilon prime is the real part of the permittivity, and epsilon double prime is the complex part of the permittivity. All right. So, and for attenuation, for electrical field with the lossy media, your alpha is not zero anymore, so it becomes this equation over here. And for H, if we use this equation we learned before, it becomes this one here. So this is your magnitude here. So this is the magnitude, and this is the magnitude. These are both magnitude, right? So magnitude in a lossy media is decreasing as your Z is increasing, because alpha is not zero anymore. All right. So and also there's a intrinsic impedance for lossy media. This component is added because this is not zero, right? Before it was not there. This all simply square root of mu over epsilon, but now we have epsilon double prime in there. So this is the intrinsic impedance of the lossy media. All right, so let's see what happened. So now, if we follow this equation over here, right? This is the impedance at any point. This is the impedance as z equal to 0, right? Then this is the way is decreasing. So if you take the ratio of that at z equal to 0, right here is z equal to 0, right? This ratio is 1, right? And you go down, it's exponentially decreasing with this value. So at some point, this ratio would become exponential negative 1. At some point, it's going to become exponential negative 1. So over here, magnitude of that over EX0 becomes, at some point, is exponential negative 1. And at that point, you can find a value, it's called delta S or skin depth, that would be 1 over alpha, right? That would be 1 over alpha. What is this skin depth telling you here? It's telling you that distance, this distance, delta S, called the skin depth of the medium, characterize how deep an electromagnetic wave can penetrate into the conducting media. So what this means, if you have a conducting media between in your propagation path, so how far your wave can penetrate into that media. All right, it could be air, could be vacuum, could be dielectric material, or it could be any conducting media. So how far it can go in there? What does it mean? So at this point over here, when alpha or delta S is 1 over alpha, so let's see here what's happening over here. At this point over here, when your Z is delta S, right? This is the Z, right? This is the exercise. This is delta S, right? At this point, your EXZ, it becomes exponential negative 1, right? So that means it's become 0.37 EX0. So that means you have only 37% of the signal you had at point z equal to 0, all right, at z equal to delta S. Now if you have z equal to 3 delta S, if you do the same math over here, your EXZ, this signal would be negative 3 EX0, right? That's become 0.05 EX0, right? So that means you have only 5% of the signal you had at z equal to 0 at the distance of z equal to 3 delta S. And what is delta S? Delta S again 1 over alpha. What is alpha? you have to find the alpha from the equation I gave you before. Alpha is right here. That's how you get the alpha for a medium, okay? So if you know the alpha, if you know the alpha of your medium, now you can calculate your signal strength at every point of your propagation. And if you have z equal to 5 delta s, your signal become only 1%. So exz at 5 delta s is become 0.01 ex0. So how quickly is decreasing as you go through the transmission line. So that's why you don't want any conducting media for your transmission line, right? So this is the big chart over here, alpha, beta, and eta c, who's intrinsic impedance of the media. So over here, alpha is any media. Is lossless media, alpha is 0. That means there's no attenuation. There's low loss media. This is the good conductor. All right. So good conductor is not a good thing for a media to propagate your signal. All right. And beta also there, and eta c is there, who's intrinsic impedance. All right. All right. So now we're going to do this example in the class to understand better how it works if you propagates through a lossy media. All right. Now, second thing is the power density. What is the power density? Your signal carry power, right? Your signal carry power. So this will tell you the flow of power carried by an electromagnetic signal. Oh, wave. All right. So how much power is your wave is carrying? That's the power density. So power density S is given by E times H. E is your volt per meter, you know that. H is amp per meter, so it becomes watt per meter square. So it's S is a per unit power density. So if you have an area that you need to know how much power going through that particular section of the area, you have to take the integration over that area. So why this two vector here? So this is the propagation direction. So propagation direction, that's why the power should be carrying. There's the incident, how is your wave is hitting that particular area, incident. So you have to take projection of this with this direction. That's why it's a dot product here. So that if you do dot product, your average power, your average power density would become, if you take this this one here and take the real value of them and take half of it, that's your average real power going through a particular area carried by the wave. Then if you have your E over here, then you also know that you can easily find H from there, right? That will be 1 over eta negative x hat E y0 y hat E. We have done it in the beginning of the chapter over here, exponential negative j k z, right? So now you have both H and E. Now if you apply this equation over here, you just learn as a average is half phasor of E cross H conjugate, right? Then you will find this equation. This is for the lossless media. If your power going through lossless media, this is the power density for that lossless media, which is watt per meter square. Right? If you go in the lossy media, you have same equation over here. Lossy media, alpha is not 0 anymore, so alpha became a part of it, right? Then if you go to the lossy media over here, then your average power going to a unit area is become this equation over here. All right. So now look at here. Your alpha is here. Your now is not eta, is eta c, which is intrinsic impedance of a conducting media, and your alpha is here, right? So that's the difference between this one and this one. This one, there's nothing in there because it's lossless media. They have lossy component all over here. All right. So that's the two equations you can give you how much power your wave is carrying through through the particular area, and also at what distance over here. Distances matter for loss emitter, because as you go more and more distance, you get less and less power carried by the wave. But here, it doesn't matter the distance; it's all everywhere is carries the same power because there's no losses. All right. So again, we're going to do this problem in the class to understand better how it works. I think that's all for this chapter, chapter 7, and we're going to get to chapter 8 soon. I'll see you in the class to discuss the problem solving and application.